Welcome to Trigonometry 6.4, the inverse of trigonometric functions. Today we're going to look at inverse functions and do a little bit of evaluating. Some of this will be a little bit of review because we have done some of this in the past. We begin by taking a look at what it means to inverse functions. Basically, inverse functions means that the x and the y values switch roles. So far in this chapter we've been working with y equals the sine of x and looking at a graph where our x-axis is angle values either in degrees or in pi form, and our y-axis are the actual trig values. If we switch the roles of x and y, graphically speaking, what this looks like is that now the x values take on the role of trigonometric values, whereas the y-axis take on the role of degrees. We will not have to graph inverse functions. This is just background information to give you an idea. Inverse functions is basically x and y switching roles. You have worked with inverse functions in this form before when we've solved for triangles. And so now we're going to evolve to go from this form to this form. Please take a minute to record the inverse functions that we're primarily going to work with: the arcsine, the arccosine, and the arctangent. The prefix arc is just a designated prefix that symbolizes the inverse. So this notation here means the same as saying arcsine. It's just more of a formal presentation of the inverse. If you recall, when we were solving triangles and we had a situation such as sine of theta equals 3 over 5, if we're solving for the angle, we had to move the sine function over to the other side of the equation. When that happens, you're inversing the sine function. And so basically today what we're talking about now is, instead of saying sine to the power of -1, we are just going to call it arcsine as a new notation for our inverse functions. Here are a few more examples of the exercise of writing our inverse functions in arc form. So in example A, x equals the sine of theta, if we're trying to isolate theta, we're moving the sine function to the other side. This is going to become arcsine of x equals theta. If we're isolating this angle here, alpha, we're moving the cosine to the other side. We're going to have alpha equals arccosine of 1/3. Tangent of y equals -3. If we're isolating that angle value there, y equals arctan of -3. So here are more examples of reading values off of a graph and using our calculators. So we've done a little bit of this earlier in the chapter. We're looking for specific angle values, in this case between 0 degrees and 360, and we're basically joining together the help of the calculator and the graphs. So in example A, x equals the arcsine of 0. Here I'm allowing you to actually get into the calculator and use your inverse function, the inverse sine of 0, to find the angle value. And I think if you try that, take a minute to do that, you'll get 0 degrees. So that is one of our angles, which falls in the interval 0 degrees to 360 for the arcsine of 0. The next step is to refer to the graph to find any other angles in between 0 and 360. And again, you've done this before. So here is that angle that the calculator found us, right at 0 degrees. Then the graph shows us that we have another place where the y value is 0 and another place here where the y value is 0. So we've got 0 degrees, we've got 180 degrees, and we've got 360 degrees. for the arc sine of 0. The next example is x equals arctan of 1. So again, picking up the calculator and doing the inverse tangent of 1, that will get you an angle value of 45 degrees. So on our graph, 45 degrees here is somewhere to the left of 90 degrees. If you look at that y value and go straight across the graph, you're looking for other angles that's in the same position as the 45 degrees that hits the 1 on the graph. So, and it's got to be between 0 degrees and 360. So we've got one of those angles right after 180 degrees. The next one is down here, but it's after 360 degrees, so we're not going to want to include that one. So how do we find the angle after 180 degrees? Basically, you're just using a little bit of symmetry. So noticing that 45 degrees is 45 degrees over from where the tangent curve crosses right on the x-axis, so from 0 to 45 degrees, we can use that same symmetry to say that from 180 degrees, go over 45 degrees, and that will give you our angle value. So quickly taking the calculator, 180 plus 45 gives us the second value for the x for the arctan of 1. In example C, we are asked to find the angle values for the arc sine of square root of 3 over 2. So in the calculator, you'll want to carefully input that inverse sine. Square root of 3 over 2. And you should find that that will give you 60 degrees. So 60 degrees on our graph is the corresponding angle for the square root of 3 over 2, which is somewhere below 90. If we continue looking across on the graph, you will see that at square root of 3 over 2, there certainly is another angle here at this point on the hump. And that will be the only one other angle between 0 and 360 that is an answer for that specified interval. So how do we find that angle value? It's very similar to how we answered that question in part B. So using symmetry for the sine function, the calculator gave us 60 degrees. You can look at it from how far away is that value from 0 or how far away that value is from 90. Either way should work. So if we say that from 0 we go over 60 degrees, we can do the same with the symmetry starting at 180 and going down 60 degrees. Okay, so if we do it that way, we'll get 180 minus 60, which is 120 degrees. We could have done it in terms or in reference to 90 degrees. So from 90 degrees, 60 degrees is 30 degrees south of that or to the left. So 30 degrees above 90 would be another way to get that same angle, 120 degrees. Okay, so find the first angle on the calculator and then go to your graph, see where that angle is supposed to be, and find any other angles in that specified interval using the graph.